Calculate the initial concentrations of the reactants. The rigid reaction vessel has a volume of 2.0 liters, into which 1.0 moles of CO and 1.0 moles of H2 are initially pumped. Using the molarity formula, M equals N/VCO0 is equal to 1.0 moles over 2.0 liters equals 0.50 molar. H2, 0 is equal to 1.0 moles over 2.0 liters equals 0.50 molar. CH3OH, 0 is equal to 0 molar. No product is initially present. Determine the direction of the reaction shift to reach equilibrium. Because the initial concentration of the product CH3OH is 0 molar, the initial reaction quotient, QC, is 0. Since QC less than Kc, where Kc equals 14.5, the reaction must shift in the forward direction to establish equilibrium. This means reactant molecules must be consumed to form product molecules. Set up an ICE, initial, change, equilibrium, table. Let X represent the change in concentration of CO as the system shifts forward. Because the reaction shifts forward to reach equilibrium, X must be strictly positive, X greater than 0. Using the stoichiometry of the balanced equation, CO initial equals 0.50 molar, change equals X, equilibrium equals 0.50, XH2. Initial equals 0.50 molar. Change equals -2x due to the 2 to 1 stoichiometric ratio. Equilibrium equals 0.50, 2x CH3OH. Initial equals 0 molar. Change equals plus x. Equilibrium equals x. Compare the equilibrium concentrations of H2 and CO. Compare the algebraic expressions representing the concentrations of both reactants at equilibrium. CO EQ equals 0.50. X H2 EQ equals 0.50. 2x, because x greater than 0, as the reaction must proceed forward. Subtracting 2x from 0.50 will always yield a smaller value than subtracting only x from 0.50. Mathematically, 0.50, 2x less than 0.50, x H2, EQ less than CO, EQ therefore. At equilibrium, the concentration of H2 is strictly less than the concentration of CO, which identifies option B as the correct answer. The correct answer is option B, H2, less than CO.